Welcome to video lecture M8. This one is on matrix inverses, properties of matrix inverses, something called elementary matrices, and an algorithm that will let us compute the inverse of a matrix. I'm your navigator, Tom Roby, and here are the outline and objectives. We want to first analyze some algebraic properties of matrix inversion that will help us understand actually row reduction in a new way. And then once we have those properties, which are very easy to show just from algebraic pushing around symbols, then we'll reconceptualize row operations as multiplication by sequence of elementary matrices. And once we've done that, that'll allow us to create an algorithm for computing matrix inverses. So it really shows the power of taking a more algebraic approach even to something that's really a very algorithmic process. And that's something that you might find useful somewhere else as well. But here are some easy propositions of inverse. But we have to always be a little bit extra careful with matrix multiplication because it's not commutative. So suppose I've got two invertible matrices, A and B. N by N matrices, they're square, they have real entries. Then if I want to know, well, if A is invertible, it turns out that its inverse is also invertible. Okay? And in fact, the inverse of the inverse is the number itself. Now, you're not too surprised by this, right? If you took the reciprocal of 7, you get 1/7. You take the reciprocal of that, you get 7 again. As long as you're not trying to do this with 0, you're fine. But you know what's going on here, right? The definition of invertible means that if A is invertible, then that means that there exists A inverse, right? So A inverse equals A inverse A. And those are both equal to the n by n identity matrix, right? So now if I want to know, is A inverse invertible, I think, well, I need some matrix B so that B times A inverse equals A inverse times B equals the identity. It looks like A actually is a pretty good candidate for that, right? So I can just let A be, so A clearly satisfies the properties that it needs to be an inverse of A inverse. So therefore, the inverse of A inverse is equal to A, right? So it just follows from looking carefully at the defining equation of an inverse. Okay, nothing deep you need to think about. Now, of course, if you actually tried to do this algorithmically, it would be kind of mysterious. Why, when if once you see the algorithm, you'll see you'd be doing a lot of work, and it wouldn't be clear at all. All right, now suppose I take the transpose of a matrix, and I want to know what its inverse is. Well, it turns out that I can just take the transpose of the inverse. So the inverse of the transpose is the transpose of the inverse. And why should something like that be true? Well, if you start from A inverse equals the identity, then we can use the fact, right? We can take the transpose of each of these things. And of course, the transpose of the identity matrix, which is just ones on the diagonal and zeros elsewhere, is itself, right? It doesn't change at all. All right, now what do we know about the transpose of the product of two matrices? We know it's not actually equal to A transpose A inverse transpose. AB transpose is not A transpose B transpose, it's B transpose A transpose. Okay, so we need to switch the order here and say, okay, then this is A inverse transpose times A transpose is equal to the identity matrix. Okay, but now I have what I want, right? The defining thing for an inverse is that the inverse of something is the thing that I multiply it by to get the identity. So what do I multiply A transpose by to get the identity? Well, the transpose of the inverse, right? So that's just saying that A transpose inverse equals A inverse transpose. Actually, I've only done this on one side, right? In theory, I'd need to show it on the other side, but you can use the other part of this equation and do the same argument to show that it works on the other side as well. Okay? So that's the proofs of 1 and 2. And now finally, if I want to think about if AB is invertible, then is the inverse of AB equal to, why should this be B inverse A inverse? It's kind of like that property for transposes, and sort of for a related reason, which I won't get into right now. But, okay, I want something that I multiply AB by to get the opposite. So if I take, to get the identity, right? So if I take AB, what can I multiply it by to get the identity? Well, actually, A inverse B inverse doesn't look so good, remember, because I can't change the order of things. But B inverse A inverse looks pretty good, right? Because by the associative property, I can just think of this as A, B inverse, A inverse. Okay, and so that's going to be BB inverse is just the identity, so I've got the n by n identity matrix in here, which I can forget about. And so I end up with just A inverse, which is equal to the identity again. Okay? So if I multiply AB by B inverse A inverse, then I get the identity. And you can easily see if you do it on the other side, you also get the identity, so it's a two-sided inverse. So therefore, the inverse of a matrix is the product of the inverses in the opposite order. And I'd like to highlight that because we're going to need to use it right away in the next slide. So if I take, this actually generalizes. This is something, you would prove it by induction. You know, you've got it for the case n equals 2, and then if you, k equals 2, and then if you just add another one, you can do the same kind of, do an inductive argument. So I'm not going to get into how we do that here, but it turns out that the inverse of A1, A2, dot, 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 AK, that product, is just AK inverse, AK minus 1 inverse, and so on. So I just take the product of the inverses in the opposite order. Okay? So if you understood why this is true, then this should make just as much sense. Right? I mean, you could sort of show it by just multiplying out and not worrying about being formal about your dot, dot, dots. Okay. So let's see, maybe I have room to not erase here. An elementary matrix, this is a new concept now, is one obtained from the n by n identity matrix by a single row operation. Okay? So let's look at some examples here. What would that mean? So take a look at these examples and tell me what you think, what elementary row operation did I apply to the 3 by 3 identity matrix to get E1 or E2 or E3. I'm only allowed to do one, right? So maybe, probably you see that, well, for this one, let's look at E2 first. What happened is now this 1 became a 4, right? So I guess I rescaled the whole row. It's a row operation. I rescaled the whole row by 4. Okay, that's a good elementary row operation. How about this guy? Well, it looks like this one's in the right place, but these guys, if I swap their order, they'd be in the right place. So that means that this is interchanging rows 2s and taking the identity matrix and interchanging rows 2 and 3. Okay? This one is take the top row, multiply it by -2, and add it to the third row. Okay? So each of these guys represents one of our standard elementary row operations. And here's the key thing, and it's really kind of fun. Right? What happens if I apply one of these guys to a generic matrix? Right? So if I do something like apply, let's just look at, say, 1, 0, 0, 0, 4, 0, 0, 0, 1. If I multiply that times just A, B, C, D, E, F, G, H, J. I don't like using I because you might think I mean the square root of -1. And so if we do this, what happens? Well, here, often, when I'm just trying to compute an example, it's often best to just do row-column operation because I can write my answer down row by row. So I get 1, 0, 0 times this just gives me A. 1, 0, 0 times this just gives me B. 1, 0, 0 times this just gives me C. 0, 4, 0, well, I'm going to get 4D, and then 4E, and then 4F, and then here I'm just going to get G, H, J. Okay? So multiplying, so this multiplying on the left has to be on the left, not the right. It's not commutative. This matrix by this by this elementary matrix did the same thing as the rescaling row operation, right? Okay? And you know, I'll do one more of these just so that you can see it. What happens if, for example, we did, let's look at E1 times this. So if we multiplied instead 1, 0, 0, 0, 1, 0, -2, 0, 1 times A, B, C, D, E, F, G, H, J, what do I get? Well, I'm not changing the top row, right? Because I'll just dot this with this, and I'll cross, and I'll get A, B, C. Now here, again, I'll get D, E, F. But now here, I'll have -2 times this plus this, right? So I'll get, I don't know, G minus 2A, H minus 2B, and C minus 2J. Okay. Right? And so I'll let you check this last one, that one does exactly what I'm claiming. It'll just interchange these two rows of the matrix. Okay? So this is very exciting because it allows us to replace something that's algorithmic with something that's algebraic. And so now here's the next thing to figure out. from this we can see that every elementary matrix is invertible. Why? So you could have paused there if you wanted to, but it should be invertible because what would the inverse be? Like if I interchange rows 2 and 3, what's the inverse of that? Well, just switching them back, right? So in fact, this is actually its own inverse. But for this one, if I rescale row 2 by 4, what's the inverse of that? Rescaling by a fourth, right? So if I just replace, so the inverse of E2 is going to be the matrix 1, 0, 0, 0, 1, 4th, 0, 0, 0, 1. E3 is its own inverse, and the inverse of this matrix is going to be what? Well, we subtracted the first row from the third row, so we'll add it back, right? So if I replace this negative 2 with a 2, then I'll have 1, 0, 0, 0, 1, 0, 2, 0, 1. That'll be the inverse. So every elementary matrix is invertible, and it's easy to see what it is. It's just the whole point is that row reduction was a reversible operation because each step was reducible. What that means in our current context is that every elementary matrix has an inverse which represents the inverse row operation. Okay? So here's a really powerful theorem, and it's not hard to see or understand. A matrix, an n by n matrix, is invertible if and only if it's row equivalent to the identity matrix. Okay? And in that case, any sequence of row operations that takes A to the identity matrix, it'll also take the identity matrix to A inverse. And this is what will let us get an algorithm. Okay? So why should that be true? So let me write a little bit down to explain all of this. I guess I'll go back to blue. Right? So A is invertible implies that, AX equals B always has a solution. Right? And, okay, we have an n by n matrix, and it's always solvable, right? In fact, the value of x is just A inverse times B, right? Okay. So that means, but by row reduction, that means that there's a pivot in every row of A. And because it's a square matrix, that means there's a pivot in every column. Okay? So this implies pivot in every row, implies pivot in every column, implies that it row reduces to that the row reduced echelon form of A is just the n by n identity matrix. Okay? So that means that A is row equivalent to IN. Now, on the other hand, I really need to show this both ways. So let's suppose that I've got a situation where, okay, I need to start writing here. So A, when I do this row reduction, what happens? A goes by some elementary row operation to E1A. That goes to E2 E1A, right? And every time I do a new one, I'm multiplying on the left by a new elementary row operation, and you just keep going until eventually you get the identity, right? And when you get the identity, that's going to be EL minus 1, ... product of these row operations times E1 times A, and that's equal to the n by n identity matrix. Okay, but now we're really happy, right? Because we can just multiply both sides of this equation by A inverse. Okay, so now you really can't stop me. I'm all set. You can't stop me from multiplying both sides by A inverse. So what happens when I do that? When I multiply, and I'm multiplying on the right here, of course, for the identity it doesn't matter, but when I multiply on the right, this AA inverse just goes away. So I end up just getting the product EL minus 1, E1, is equal to A inverse. Okay? And now, the last thing that you can't stop me from doing is I'm going to just put a little IN in here, right? Because when I multiply by IN, it doesn't change anything. So when I multiply EL minus 1, E1 times the identity matrix, I get A inverse. So that means exactly that applying that sequence of row operations to IN gives me A inverse. And it also shows that this is invertible, right? I mean, we already knew at this stage that it was invertible because we had a product of elementary matrices times A was the identity. And that, I guess that's another way to see that elementary matrices are invertible. Okay? So in the next slide, we'll see how to turn this into an algorithm. So how do we make an algorithm out of that last theorem? Well, what we do is we say, take your n by n matrix, and now we'll make an augmented matrix, but it's like super augmented because we're going to augment it not just by a single column, but by n columns. So on each side of this vertical divider, we'll have n columns, and we're going to row reduce. And when I row reduce, I have to apply my operations to all the rows of the matrix all at once, of this all 2n terms in each row. And I row reduce it until A is in row reduced echelon form. Now, if I get the identity matrix, then whatever I get on the right-hand side when I do this sequence is the inverse by the theorem. Because the same sequence that of elementary matrices, of that product of elementary matrices, that is essentially what I'm doing when I apply this, that got me to In, is the same one that takes B to A inverse. That's what the theorem says. On the other hand, if I get something that's not In, then that meant that the matrix couldn't have been invertible in the first place, and it doesn't matter what this B is, it's irrelevant. And in that case, A is not invertible. So that's all very abstract. Let's take a look at a concrete example here. So suppose I've got 1, negative 3, 0, negative 1, 2, negative 1, 0, negative 2, 2. That's my matrix that I want to invert. And now I've augmented it by the 3 by 3 identity matrix. And I'm just going to do all of this for you. You can always just see the punchline on the handout of the slides if you want, and ignore the rest of this if you want to. But I'll try to say things that are useful, and it's always good practice to do some row reduction. So here we go. So let's think. What should I do first? Looks like the first thing I want to do is add row 1 to row 2, and then that whole column will be zeroed out. So what do I have to do? So it's going to take us a couple minutes to do this, but it's worth doing, and I'll try to say useful things. So I don't change the first row. The second row, I have to add the first row to it. So I get a 0 here, I get negative 1 here, I get negative 1 here, and now I get 1 here, right? 1 here and 0. And now I haven't changed the third row, so I just carry it along. And I'm really doing this. I'm not just copying from a teleprompter. Okay, so now what happens? Well, I want to zero out this negative 1, and unfortunately this is a negative 2. So I guess I'm just going to have to bite the bullet and, well, actually, no, the first thing I want to do is I want to make this a pivot. And so I think what I'm going to do is, well, let's rescale. If I multiply by negative 1, then I can do that. And that all happens without me having to write everything else out. And now I'll use this pivot first to zero out these guys, okay? So let me leave row 1 alone. And so I've got 1, negative 3, 0, still 1, 0, 0. And now, since I'm using this rescaled row 2, that looks like that. And now I'm going to multiply by 2 and add to this, right? So what happens when I multiply by 2 and add? So I'll get a 0 here, multiply by 2 and add. I guess I'll get a 4 here, multiply by 2 and add, negative 2, multiply by 2 and add, negative 2, multiply by 2 and add, leave it, just stays 1. Okay? So that looks good, right? And now, okay, so now I'd rather, before I add this one up here, and I've already got this to be a 0, so I think it's going to be more efficient if I use this pivot to get rid of that. Okay, so how can I do that? Well, I think I'm going to do a better job of it if I just bite the bullet and go with the fractions. And sometimes you get fractions in these things. So the next thing I'm going to do is rescale this guy. So nothing will change here. But here I'll have 0, 0, 1, negative 1/2, negative 1/2, 1/2. Okay, now things aren't lining up so well, but I'll try to do a better job next time. All right, so now what's the last one that I can fit on this row? So I'm going to multiply by negative 1 and add here to zero this guy out. Okay, so top row stays the same. I need to leave more space, even though it doesn't look like it at the top. Now, this row is going to stay the same. But I'm changing the middle row by multiplying by -1 and adding. This becomes a 0. Multiply by -1 and add. This becomes -1/2, right? Because it's -1 plus a half. Multiply by -1 and add. This becomes -1 plus a half is negative. Okay. Good. So now I just keep going. All right, what do I want to do next? Thinking about it strategically. So this is good. Now I just need one more step and I'll be done, right? I just need to multiply this row by 3 and add it to the top row. Okay, so what's going to happen when I do that? So when I multiply by 3 and add, well, I'll just get 1, 0, 0 there. So that's easy. 1, 0, 0. And now over here, multiply by -3. Now multiply by 3 and add is what I'm doing to zero this out. So I multiply by 3, I get 1 minus 3/2 is -1/2. And now 0 minus 3/2 is -3/2. And 0, and then it's -3/2 again. Right? I hope. And so then, these guys, so now it's 0, 1, 0 times -1/2, -1/2, -1/2, and then it's 0, 0, 1 times -1/2, -1/2, 1/2. And so now, I have this vague feeling that this isn't the same answer I got before. Right. So I made the mistake here. I divided by 4, and so this guy should have been 1/4. Okay, so I'm going to correct it everywhere. So this is good. You get to see me actually make a mistake. And so now, let's see, here I didn't. So how did we go? How did this guy become this? It's because we added -1 times this to this. So when I added -1 times this, so when I added -1 times this to this, I should have gotten, I guess it should have been -1/4, right? So this should have been -1/4. And then that mistake propagates through here where this was 1/4, this is -1/4, and then when I multiplied by 3, I should have gotten -3/4, I guess. Okay, that looks more like what I got before. Good. Okay, so now I'm done, right? The inverse of this matrix should be this matrix. Now there is one trick here, which is that if you've got a kind of scaling factor here, there's basically a 1/4 floating around in here. And the way to make this better is to say, okay, so then this matrix A inverse, what's it equal to? Well, it's actually going to be equal to 1/4 times something. And let's see what that something is. So if I multiply every entry in here by 4, because I'm factoring out a 4th, I'll get -2, -6, -3, -2, -2, -1, -2, -2, 1. Okay? And -2, -2, -1, -2, -2, 1. Yeah, so I think that's right. And of course, how can I be sure whether this is right or not? So let's see. Oh, well, first of all, I can show you what I got there. So that's actually the correct answer if I don't have a typo there, but it looks like it matches what I got. And now, of course, we need to check. So how do we check? Well, let's just take a different color here and say, okay, what happens if I multiply this matrix times A now? Okay, so let's multiply this matrix times A. So A was 1, -3, 0, -1, 2, -1, 0, -2, 2. You should always check your answers. in my classes, I always give students extra credit. If they check and they found that they made a mistake, they get way more credit than if they didn't check at all and just assumed their answer was right. So even if they didn't have time to go back and repair it. So let's just check row column operation. So -2 plus 6 is 4, plus 0 is still 4. I divide by 4, that first entry turns out to be a 1. Okay, so it looks like I get a 1 there. I'm not going to do all of these because it would be tedious, but let's just do, say, let's do something that shouldn't be 1, right? So let's do row 2 times column 3. So that would be the 2, 3 entry. That's this one. If that's the only one I want to compute for the moment, then I get -2 times 0 is 0. -2 times -1 is 2. -2 is 0. And so if you keep doing, I'll do these all really fast in my head. Oh, look, I get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So it checks out, and this is the inverse. And so that's how you do that's how you actually compute the inverse of a matrix algorithmically. It's just using row reduction and making the super augmented matrix. And it all comes out of this beautiful theory of elementary matrices. So that's it for this lecture. Thank you for your kind attention.